Hello, I'm Josh, and I'm here to speak a little bit about architecture and routing in a geopolitical world. And my supervisor is also here if you want to ask questions at the end as well. So without any further ado, we've got a few different ways of looking at what the internet looks like. And I'm sure some of you have seen at least one of these different versions of it. So one of them's looking at the AS core and how autonomous systems interact on the internet. One of them is looking at kind of what part of the internet is hosting how much content. And there's sort of other connectivity maps through time as well. Some of these have some advantages, others have others. But importantly, why should we care? And here's an example. For instance, we all have our own priorities of what we want an internet to look like. From a user perspective, that might be really low latency. From an operator perspective, that might be sort of network routing transparency, so you know where content is going, how you can steer it. And also settlement-free peering is a sort of economic incentive so that everyone is able to provide transit. So arguably, this might be to some people a kind of border-free, settlement-free, transparent, and uncensored internet, which, of course, we all know is not the reality. And so this is kind of touching on that, looking at the kind of geopolitical element. So kind of within the context of internet sovereignty, where nations are trying to exercise what they would call a right to govern their networks to serve their national interests. In the UK, we call that making the UK a safe place to live and work online. In other countries, there are kind of other implementations. And then there are kind of governance ideas being shared. So I know Netman Dial was only a week or so ago now, and they had their own outcomes and their own vision for how the internet should be governed. So alongside that sort of angle of it, there's also increased regulatory intervention. So at each one of these kind of content, platform, and network levels, different countries are introducing different types of legislation. Across the EU, they've got some examples. Here in Poland, there's some legislation to go almost to counteract some of the EU examples. In the UK, we've got the new Online Safety Act. So everywhere is kind of starting to build even more of a kind of regulatory base for the internet. And of course, that can't be implemented in a kind of borderless internet world. So there are kind of three questions I want to look at a little bit here. So first of all, there's like, does the topology differ between countries? Do different countries' internets look slightly different? How does it differ? And then why might it differ? So looking at whether that legislation might actually be kind of the impactful element. So our work is kind of building a tool to collate internet topology data from a number of different sources and compile it into a kind of internet topology graph that we can analyze and then possibly do other things with. I've got a link on here that take you to our sort of lab website, and hopefully next week I'll release the source code for this as well. I just need to clean it up because I've been running it on a specific machine, so I need to make it a bit more platform agnostic. So first of all, kind of looking at the approach that we take, I want to talk you through a little bit about what this tool does. And first of all, it's taking sort of internet routing data from a variety of different sources. So route views from the University of Oregon, the RIPE NTC's RIS service, along with RIPEstat and a couple of other tools like Atlas. And then the packet clearinghouse, which provides sort of dump data from a number of routers, various internet exchanges around the world. So another quite a rich source to try and expand what we can see. And this is kind of how the system works. So we take in kind of internet routing data from these route collectors. We take in metadata, so things like the registered country, the registered location, who owns the resource, and whether they own any other resources, and we process that in. We also look at kind of geolocation data, so can we see where a given router is in the world, and that way we can kind of start to detect ASs that span multiple places. And then we process this data, we label our internet topology graph, and then we use this to output. So when it comes to capturing location, there are a few different challenges. One of them is that different registries capture that data under a slightly different field. And also when it comes to networks spanning multiple locations, the different AS tags that come associated with that are also quite interesting. And then another part of this is kind of looking at prefix geolocation. And in our case, we're using MaxMind because it's a free source for our research. But it also comes with some of the like cyclical dependencies that if they don't know where something is, they just use the registry information anyway, which doesn't necessarily give us any additional richness. adding additional metadata to this. So we take in the registered owner, but then we have to try and work out if that owner exists in another autonomous system record. So for instance, if a company is merged with another one, often there's an inconsistency in the data despite the company ultimately being the same. So we have to try and look at that. So we're using things like peering DB, opaque IDs, and that kind of thing to see if we can correlate between the same owner across multiple registries. Also looking at the registered location, this is using ISO standard country codes, and so I'm going to keep that consistent throughout this. So whenever you see a country code, that's the ISO standard one. I haven't made up a new additional one. And then looking at state ownership data to see if the state owns a percentage or more than 50% of some of these companies that we detect within the data. And then ultimately, we get this as an output. So we get a node being an autonomous system, so with an autonomous system number and associated metadata. And then an edge is just an adjacency between it that we're detecting with things like AS path and also some trace route data from ripe atlas probes. And here we go. Here's a basic example, just a general node-to-node peering, so an AS to AS. So if we look at 2024, this is coming from the 1st of May, and my timestamp start point was at midnight, so the start of the 1st of May. We see 84,266 autonomous systems, and to give you a bit of a comparison with alternative data sources for the same time period, I put ours. We've got how many ASs reserved within RIS, and we're a little bit higher than that because we've combined a number of different sources. And then to try and give you a comparison of what kind of adjacencies we're inferring from that data, I put our data for 2024, which is a little bit higher on the right-hand side here with a blue-like graph line, and then ours versus Kinda's in 2020, because Kinda probably has the richest set of data for kind of inferring interconnections. So you can see we've got a little bit of progress on where we were before. So our topology is seeing a little bit more, and part of that is to do with the richness of the data sources we're combining to build a better data set. In particular, we know that our data isn't quite as accurate for Africa because there's very little in the way of root collecting probes in Africa. So if anyone can advocate for that, that'd be really helpful. Within the same time, we're seeing 84,266 ASs. We're also seeing 116,977 NRO assignments. So that's the maximum, I guess, number of potential ones if you're excluding bogons that could be in the data set. This is only the ones we're seeing as active. So in reality, that number would be slightly smaller, but clearly we're not seeing everything. And that's kind of an overview of how rich our data is. And this is what we see for it. So in this case, we've got a CCDF plot of the maximum degree, and that's running along the bottom. And then vertically, we've got the kind of probability on a log-log scale of seeing that. And so this is showing it across 4 different periods of 2010, 2015, 2020, and 2024. What's particularly interesting, though, if I look on this next slide, is the kind of decrease in the medium degree nodes between 2023 and 2024. And then seeing a higher number of high degree nodes. So this is talking at nodes with a degree of like more than 10 to the 3. And that's an interesting trend that we're kind of starting to see this like medium number decreasing and the highest degree nodes increasing. So an interesting discovery there. Also, if we look at like RPKI deployment on the same scale, we're taking RPKI deployment as where we can see one ROA object for the AS, which I appreciate is not possibly the best measure of it, but it's one way of looking at it. And so on here, we've got all ASNs, so we can see that's the purple line going through, and then we can see the number of medium degree nodes where they've deployed a RPKI is much higher, but at high degree nodes, there's possibly a little bit less on that front. And then when we've seen no RPKI, we're seeing that mostly existing still within that medium degree node space. So the probability of encountering a non-RPKI deployed node, you're going to get a degree between 10 to the 1 and 10 to the 3. So 10 and 1,000. And then if we look at the average neighbor degree, so this is taking the average degree of all of an AS's locally collected peers that we can see. This is another interesting plot, which kind of shows that at the higher end, where the average neighbor degree is right above 10 to the 3, the number there has been increasing over the past kind of 4 time periods, so 4 lots of 5 years. So another interesting kind of key trend. And then this is a kind of crude way of looking at it, but most influential, where we talk about eigencentrality, which is how kind of central to a network graph a node is when it comes to an autonomous system. This is the kind of top collection of autonomous system providers that we can see based on our company data. We know our data is slightly biased because a lot of the root views and RIPERIS data is collected from root collectors paired with Hurricane Electric in particular. So where we see them being like at the most central in this graph, that's possibly not true. But what we can see is that the kind of major providers that we would expect to see are appearing in that data in the most central. Then we talk about kind of autonomous systems and peerings. The number of autonomous systems registered or observed has increased significantly since the start of our data collection period in 2005. The number of public interconnections has also increased. But what is really quite interesting here is that the average path length has increased as well. So where in like a lot of particularly academic literature, we talk about an average path length being about 3.7, in this latest collection of data from 2024, and also similarly in 2023, we're seeing that path length being 12. I think there are a couple of possible explanations for that. One of them is there's a problem with our data. I don't think that's true because we're capturing the previous measurements up until about 2015 using our data as well. So there's something going on there. And I think it'd be interesting to find out quite what it was, whether it is kind of this, what I'm going to suggest is possibly kind of censorship approaches, or whether it's just an increase in private peering and we're not detecting this, but we are trying to mitigate for that with trace route entries as well. So hopefully we would be picking up much of that. So the kind of does element here, does topology differ between countries? I've got here a force-directed plot of the internet looking at May 2024. And so I've put a number of countries allocated colors in this graph on here. And you can see kind of at the top here where that green patch is emerging, that's the United States. They've got quite a strong domestic interconnected base. On the right-hand side coming out in this kind of large blue patch, that would be the connectivity of Russia. Russia's approach to censorship is quite interesting because they have quite a distributed approach. So what we see is a high degree of interconnectivity with the rest of the world from quite a lot of nodes, but we still see a kind of separation coming out where they've got kind of a domestic network that can exist almost on its own. And then coming off on the left-hand side, you get this kind of weird like spring side here, that's Iran. And we can pick that up quite clearly on the graph. And China's actually so far off this graph, we can't see it, and it goes out the bottom edge. So it's an interesting kind of way of seeing that the interconnectivity of some countries, and particularly the United Kingdom, where I come from, is right in the middle of this graph, so you can't even distinguish it. And then some of these other countries are quite prominent. And then the how. To look at this, we want to look at kind of what a foreign neighbor is. So this is kind of how we're calculating it here. So we have the registered location of these autonomous systems. And so on here, we have like Not Company LLC is in the UK. It relies on its upstream provider, Internet Provider Limited, which is in the UK. And then following that is connected to what we're going to call a foreign neighbor. In this case, it's going to be Hurricane Electric, which is in the US. So that's how we're defining a foreign neighbor, would be the foreign neighbor of Internet Provider Limited. So we look at unique upstream neighbors, which is going to be the number of neighbors we haven't yet seen that are not from a domestic country and are not yet seen as we move at each step. So we're going to move from that kind of first base where we're in the UK, it's got a foreign neighbor, that's going to be the first unique upstream neighbor collection. And then beyond that will be the ones that set of neighbors are connected to that we haven't already seen. And this is kind of where we get this graph from here. So I've got a number of different countries running along the bottom. It's Norway, China, Russia, Great Britain, India, and the United States. And you can see there's a kind of a trend here with some of the countries where you'd expect higher censorship. In the first few steps, we're going to get a kind of decrease in the number of unique neighbors we discover. Interestingly, also, we get the same thing when we look at the United States, although it's not quite as pronounced. So that's a kind of interesting topological trend, is the number of unique neighbors is decreasing after a first one of these steps. And then visualizing connectivity, I'm using a graph format here where effectively in the center of it is going to be the most important nodes. And as we move further out, they're becoming lesser important. So they're not critical to the kind of domestic connectivity. When we're close to the center, we're expecting that now to be kind of tier 1, tier 2. And so if we look at this for a collection of countries, so here we've got Iran. What's quite interesting here is we're looking at the topology of Iran and its first degree foreign neighbors, and we can see where those neighbors are connected as being almost on the edge, sort of lesser importance to kind of the domestic connectivity of the country. Now I want to keep that picture in mind, and if I show you a slightly different one, this is Norway, for instance. And we see that in Norway, a lot of their domestic connectivity uh, is delivered on the outer tiers, the lesser of importance nodes, and a lot of the connectivity they have to the rest of the internet is delivered almost centrally to this graph through some tier 1, tier 2 providers. An interesting trend. And we can see this kind of reflected through a number of countries. I'm going to show you the United Kingdom here because it's a much bigger network. We're seeing again that kind of dense mass of a lot of different colors being a lot of different countries being the most central part of the network. And on the outside, we're looking at the domestic connectivity of the country that's kind of dependent on these international providers. So an interesting kind of topological phenomenon. So looking at the why is this a thing, I'm going to suggest that potentially censorship is one of the arguments there, so kind of domestic regulation in each of these countries, and a way of implementing that is to have control of the connectivity going externally. So in this case, we're using the UNI data, so the Open Observatory for Network Interference data, and there are two different ways this to kind of detect censorship. One of them is the explicit censorship, so people are seeing block pages, or we can see that the DNS resolution is just not correct. And then we've got kind of non-explicit ways where we're looking at anomalies in the data that we're collecting. But of course, we need to mitigate a little bit for that. So we look at kind of the ratio of anomalies to normal traffic or good traffic. And then I'm going to talk here about relative upstream change. And that is, again, that same phenomenon where we look at the number of neighbors going outwards. In this case, we're not looking at unique neighbors. We're just looking at the number, so the volume of ASs at each one of these steps. And we're going to look at the change. And we're looking at that from the border. So where we're talking about that, we're talking from the domestic nodes layer, followed by the first degree of foreign nodes, and then the second degree. And if we do that, we have kind of relative upstream change going up on the left-hand side here, and then the ratio of censored and anomalous to normal or okay traffic along the bottom. And we can sort of start to see a relationship as we move at each one of these steps, so degree 1 being that first step of foreign connectivity, degree 2 being the next step. And we can see that kind of trend increases. I don't want to put too many dots on the same graph, but you can start to see the trend emerging. When we kind of accentuate that, we look at what we're going to call cumulative downstream burden, which is going to be the number of ASs that are external, that are like dependent, or the country is dependent on for its connectivity domestically. So dependent on being like connectivity to the outside world. So if you're a first degree node, for instance, you're going to have a greater dependency if there are fewer also at that tier. And here we're starting to see a correlation between the two. So as the amount of interference or censorship and anomalous traffic to OK traffic increases, this kind of connectivity burden is also increasing. So there's a kind of a funneling effect here happening where nodes are being like dependent on that are further away from the country's core. And then this is kind of doing the same metric, but in this case, it's kind of removing the duplication. So if one company is owning 5 of these nodes, then we're going to collapse that to being one company because it's got sort of one rule set potentially behind it. And we see a much clearer distinction. So what we're seeing here is the higher level of censorship is equating to a higher level of what we're going to call the funneling effect, where this is kind of bottlenecking traffic going outwards from a country. And so we're seeing that for high censorship. But what's also interesting is where we're seeing high levels of funneling, you can also see there are geographical restrictions as well. So for instance, South Korea, where they've got a higher level of funneling, has neighbors that potentially aren't going to be an open internet to connect to, like North Korea or China. And so their level of funneling is much higher because they are dependent on a small amount of connectivity to the outside world. So another kind of interesting trend. Also geopolitical. So one of them is the political angle, and then this would be the geographic part. So in summary, what I've shown you here is kind of the basics of this kind of internet topology fusion tool that we're going to make open source in the next week. The degree of the highest, the volume of the highest degree AS is increasing over time, but also the volume of the lowest degree is also growing. But in that mid-range, we saw that between 2023 and 2024, the volume of AS has actually decreased. And also that geopolitics is having a statistically significant impact on the shape of internet topology. And this is a trend I would expect to continue growing as censorship in different countries is increasing. So we can see that kind of relationship is existent.